Okay, here we go. Here's a problem that you've seen in the past. It's called the concentration problem. It deals with rational functions. Now, this particular problem is dealing with a chocolate dipping dispenser. Now, I've got a chocolate fountain that has a 500-liter capacity, and it already contains 20 liters of a 70% milk chocolate mixture. So it can hold 500 liters. It already has 20 liters in it. That means I can add 480 more liters to that fountain. Now, the problem says that I add X liters of a 90% mixture to the fountain. So what's happening here, just to give you an idea, is it already has 70% milk chocolate. I want to add a 90% milk chocolate mixture. That means that depending on how much I add, my 70% concentration is going to increase and get closer and closer to 90% depending upon how much I add. We want to write an equation that's going to demonstrate the concentration of the milk chocolate as I add X amount of liters. So this is how we do this. Quite simply, you take your percentage times the amount that you have of that percentage plus another percentage times the amount that you have of that percentage, and that's going to equal the concentration times your total amount. The percent that we start with is 70%, and I have 20 liters, so 70% times 20 liters. Plus, I'm going to add 90% of an X amount of liters. That's going to give me a concentration. That concentration is somewhere between 70% and 90% of 20 plus X, because 20 plus X is going to be my total amount that I have in the chocolate fountain. Now, if I want to solve for X, I have two variables here. I actually don't want to solve for X, I want to solve for C. But if I want to solve for C, there's two variables. There's an X and there's a C. I'm going to multiply. 0.70 times 20 is 14, plus 0.90x plus, now actually equals, I was jumping ahead of myself here. I don't want to distribute the C because I want to solve for C. So I'm going to keep this C times 20 plus X. If I want to solve for C, that means I need to divide both sides of my equation by 20 plus X. And now my equation is C equals 14 plus 0.9x over 20 plus 1x. This is called a rational equation. Now, rational equations have asymptotes. I have a vertical asymptote at x equals negative 20. So I'm going to make a little grid here. I have a vertical asymptote at x equals negative 20. That is my vertical asymptote. That is not going to be part of the problem because X stands for the amount in liters that I add to the fountain. I can't add a negative amount, so that portion of the graph is going to be unused. I also have, in addition to the vertical asymptote, I have a horizontal asymptote. The horizontal asymptote is at y equals 0.9. That is extremely important in this graph. And we'll find that if we were to plot points, if I were to put a 0 in for x and add absolutely nothing, I know that my concentration, which is my output, my concentration is 70%. So this ordered pair right here is 0.7. I can add as much as 480 liters because remember, it has a 500 liter capacity and it already has 20 liters in it, so I can add 480 liters. If I put 480 liters into my calculator, I would get 0.892. So if I put 480 into my calculator, I would get 0.892. So what we would find when we graph this is that we have a portion of a rational function, that looks just like this. The reason why we're not using all of it, see it drops down here, is because in the context of the problem, x stands for the amount that we add to the fountain. We can't add an x amount, a negative amount, so that portion of the graph is not even pertinent to this word problem. So the domain starts at 0, it ends at 480, and we have this portion of the graph that we look at. Now let's look at the question that it asks. It specifically asks us, what does the concentration appear to approach as the fountain is filled to its maximum? It does not say as we approach infinity or as we add an infinite amount, what is the concentration? It says what is the concentration as the fountain is filled to its maximum. So the concentration as the fountain is filled to its maximum is 89.2%. And I hope that that's pretty clear for you, that as the fountain is filled to its maximum, the maximum concentration for this problem, because there is a limit on the capacity of the fountain, the maximum concentration is 89.2%. And that is what the concentration will appear to approach as we get closer and closer to adding 480 liters.